Dr. Cristian Suteanu is the chairperson of environmental science and professor in both environmental science and geography. He has his PhD from the Romanian Academy. Dr. Suteanu's main interests concern information processes and the ways in which they link humans and the environment. He focuses on the analysis and modeling of natural systems, structural aspects of geosystems, landslide dynamics, climate variability, renewable energy. He also studies epistemological aspects of our interactions with the environment and their implications for cultural processes. He has been published in such journals as Meteorology and Atmospheric Physics, the Journal of Coastal Research, the Journal of Environmental Informatics, International Journal of the Humanities, and Culture and Society. Dr. Suteanu is also a frequent presenter at international conferences.
Okay, good afternoon. And thank you so much for being here and for still staying. I thought everybody would leave the room after all that. We promised to have this event short. But anyway, thanks a lot.
It's up to you to make up the time.
Yeah, exactly. Thank you. Good idea. So I would like to share with you some new insights and partly unpublished insights regarding a subject I find fascinating. And of course, I'm glad to do this in this great context of celebrating 20 years of environmental science here, which is, makes one feel great. So this is about wind power and some questions that I'm asking and some assumptions that I'm questioning. Why wind power? Well, for one, we know that when something wrong happens, results are usually not as bad as what happens when accidents occur with other sources of energy. I don't know where to start, but just imagine other sources of energy and what happens with accidents. So this is one reason, but we know them all, and we know it's clean, perpetual, no greenhouse gases, no water being consumed, which is a factor that is increasingly taken in consideration. It is easily installed and dismantled according to some. Installing and dismantling a wind turbine is actually recuperated financially in 3 to 6 months, which you cannot tell about other power plants. And the wind power picture worldwide has changed in the last several years quite fast. So if you see that almost 40% of the energy in Denmark is coming from wind power now. Okay, so there are also, of course, some question marks and some limitations and arguments against wind power. Maybe the most important one, the relevant one, is intermittency and variability. This is one key subject that I'm addressing today. But there are others, of course, related to noise, related to effects on birds, aesthetic effects, and so on. But I'm not going to touch on that. So what I'm going to do is to look at this idyllic picture of safe statements, and I'm going to address 3 of them. One of them is this, that when you look at wind speed variability, looking just at the values, considering just the values, is good enough. When you see papers on variability, mostly they use statistical moments. I just downloaded yesterday one just published, so fresh, one day fresh, and they are doing exactly this, looking at variance and statistical moments. And whether this is enough, well, we'll see. On the other hand, in terms of wind direction, again, the assumption is that if you take a rose diagram and you get overall distribution of wind directions, that is what we should know. And last but not least is the almost unquestioned assumption that if wind doesn't blow in some place, it definitely does blow somewhere else. Well, when you plan on building wind farms, you'd better rely on something more than it will surely happen, right? So we are going to question all these statements, and I will do this in a way that is exciting for me, probably less exciting for those who support those ideas. But I I'm really excited about this because they are new, and when they are new and not published, this makes you really, provides a bit more energy. But no, in terms of variability, wind patterns are strongly variable. So if you think about statistical moments, well, there is reason to find them really high. So according to standard statistical approaches, when you look at statistical moments, in other words, the distribution, the dispersion of values, we can see that the dispersion is quite wide. So there are good reasons to look at this from that point of view. But let's look at these two series of numbers. And they're identical, as you can see. And now we do something to the second row. They're the same numbers, but now their sequence has changed. Now the question is, does this matter? So let's take together a test. We all know what sidewalks look like right now in some places. And let's suppose that we take this test. Sidewalk selection. Let's suppose that the mayor of Halifax asks you, what kind of sidewalk would you prefer to have? What kind of variable? Would you like a more variable or a less variable surface, ice surface to walk on? And version 1 is this, sidewalk profile 1. And the other version is this. And guess what? From the point of view of statistical moments, they are the same. They have exactly the same standard deviation because actually these are the same values. What I did was to represent them in a sorted way, so I just sorted them from the lowest to the highest value. They are exactly the same values. Being the same numbers, all the statistical measures, all the moments are the same. However, if it's about picking one sidewalk or the other, it might not be the same. So for some applications, in some cases, value sequence counts. And if this is so, then we are supposed to do something about this in this terms. So we look also at a scale-by-scale picture. And why is this important? First of all, because uncertainty is the key factor related to choosing wind power in the first place and knowing how to exploit wind power. And second, because in order to interconnect wind farms, we want to know on what we can rely, or what kind of variability would be involved at the scale of hours, days, weeks, months, and so on. So this is an image with wind patterns in different countries, in different locations, averages, and so on. And in some cases, you can see that there are similar values in all at the same time. In others, they differ. But this is not enough to say they definitely have wind or don't have wind elsewhere. We need more than that. We need a quantitative approach. So what we do in order to include these ideas in the analysis is this. We take the pattern, we take a certain time scale and slide it along the pattern and assess something. I'm not going to tell you what. That's a mystery. That's a secret. No, I can tell you about this if we want to, we can sit down. But the idea is that you assess what we call the size of the fluctuation. This can be done with different methods. One of them is called the trended fluctuation analysis. Another one is Haar wavelength analysis. The thing is that you come up with a number for each position of this window that tells you how strong the fluctuation is. Overall, you are learning about the smoothness, or if you want, the roughness of this landscape. But we do this with a larger window, and a larger, and a wider window. So we do this scale by scale. And in the end, what we get is a graph that shows us time scale, which can go from, let's say, seconds to minutes to hours to days, weeks, years, decades. And then you have the size of the fluctuation assessed on all these time scales. And the amazing thing about many natural patterns is this, that you have a continuous power law dependence between this time scale and the size of the fluctuation. And let me put just in brackets the fact that the same happens with temperatures, which make the difference between, classical difference between weather and climate absolutely meaningless. There is no difference between weather and climate on the scale from days to 90, 100 years. There's one whole continuum. There is something else that we can identify, what a researcher from McGill University calls macro weather, and then climate and macro weather. That's Sean Lovejoy from McGill. He has an amazing approach using multifractal to this, but from this perspective, only on these time scales, we can see a smooth dependence. Classically, what people do is to find the slope which tells you how rough is the landscape for the sidewalk or for wind speed. What is new now, what I'm bringing new now is this. Instead of looking at the whole graph, I'm looking at scale by scale dependence on fluctuation of time scale. So I'm getting the variability for each scale, which leads to new kind of graphs. And this is what it looks like. So here we have time, in this case it's months. Here we have the time scale, and the color shows you how rough or how variable in this case the wind is, the wind speed is. In other words, here we have with low reddish variability colors meaning high variability or rough landscape, and yellowish whitish meaning smoother values. So you can see that, for example, at a scale of 2 days there is strong variability. Here you have intervals of smooth, low variability, with very strong variability again, and so on. And you can identify scale-by-scale behavior, which is a useful and quantitative tool to feed models that would treat the way interconnected wind farms would look like. So it's suddenly something quantitative, and the scale-by-scale defined tool, I would say. What about the second assumption? Wind orientation is based just on distributions again. So what people do, and it's a nice thing to do, of course, is Rose diagrams like that. So you know how much time out of in a certain time interval, the wind blows in this direction, and so on, and with what wind speed. You can see this is quite a nice diagram. And in reality, however, wind does not blow steadily in one direction, and then in 5 hours it blows in another direction. In reality, it's more like a crazy clock like that. We know this very well, right? The wind direction is changing quite promptly. So why is this important? Because the turbine has to be aligned for the wind energy to be converted in an efficient way. For this reason, the turbine will turn, and for this it has a so-called yaw system. But this rotation takes time. For the most modern turbines, there is a so-called active yaw system, and it takes minutes for reorientation to occur. So how fast wind direction changes, and in this location or another, is important. So when you choose a location for your wind turbine, or even more so for a wind farm, you've got to take this in consideration. Now, this is what we have to do. We know how to assess numbers aligned one to the other, time series, right? But what about something like that? Imagine that we have in this spot a wind of this size, and then of this size, and this is a direction. So the length of the arrow tells you how strong the wind is, and then the direction tells you the direction of the arrow tells you the wind direction. How do you assess patterns like this? And this question has bugged me for weeks, months, and at some point I said, wow, that's the point. And it worked. You know, sometimes you say wow, and it's just that. But sometimes after the wow, you get something done. So this is the method. This is time, and for each time interval, let's suppose we take this time, we have this plane, and this is the wind direction. So what I do is to project the wind direction on a certain direction. In this case, let's say north. And we get this projection. I apologize for the cosine. It was not my intention to have it quantitative. I wanted to share with you the principle, but that's the idea, right? So for each vector, you do the same thing. So all these are vectors, right? And you project them, and some projections will be shorter, some will be longer, depending on how long the vector is and what the direction is. So we will get a new time series now with all these projections. But now we take this cactus and rotate it a little bit and do the same thing. So we rotate this vector with all these arrows and do the same thing. And we rotate it by another angle and do the same thing. And for each, the result of the resulting time series, we know how to analyze them. We use what I just showed before. For example, Harvey plate analysis. And we get an assessment of the variability or the roughness, but in this time coupled with orientation. And that's the new and exciting stuff. And we get something like that. Of course, the first plus is that you can print them out and put them on your wall. But the second plus is that it shows you something that you couldn't see otherwise. So here is direction, here is angle, and this is scale. So you see we have here 1 hour, 2 hours, 3 hours, and so on. And the colors again refer to the variability, the roughness of orientation variability, right? And you can see, interestingly enough, in all these examples, there is a threshold here around 1 hour and a half. For some reason, it is very hard to tell why this happens, but what we want to do is to assess the way it happens and to assess the best possible locations for one device or another. So in this way, we can assess at the same time wind speed and wind direction in relation to scale. So we have an assessment of variability from both points of view. And in the end, the overall goal would be to build a kind of phase space, a space in which you would have on one direction, in one axis you have the expression of, let's say, classical statistical means, moments which are useful. I don't mean to say they are not useful, but they don't capture everything. In another, you would have what I just showed before for wind speed. In another, you would have orientation and so on. And then you can follow the way the system moves or changes in space by looking at a point that rambles around in space and can say, oh, my system is there right now and this means that. Or that particular system, the wind farm in Gaspe is mainly spending its time in this corner here, which means this. And in, I don't know, in Prince Edward Island, it is mostly in this region, which means that this is the kind of pattern that we should expect, and this is the kind of design that we should have in mind. So that's the goal. Thank you so much. And these are some photo credits. Yeah. So, I'm waiting for your questions. Can I give you an answer? Another answer then? Yes. Well, what seriously speaking, I hope that this would be a tool that would improve certainty, or let's say decrease uncertainty. And what is the best thing of this approach is probably the fact that you have an uncertainty that you can measure. So you don't just say this is probably like that. You can say it is like that, and this is how probable it is that the system would behave like that, because these systems are wildly variable. Irregularity here is remarkable. If you look at the wind speed patterns at the level of the scale of minutes, the graph I showed you referred to 10 hours, but you look at the scale of months or year after year, averages of year after year, they are very similar. So having one kind of pattern this year doesn't mean at all that you'll have something similar next year. This is why I'm saying uncertainties are large, but in this way you can tell more and capture more of this variability and be able to tell it's that probable that this is going to happen like that. And then wind farm interconnection, I haven't seen studies like that so far. I'm not an expert in wind energy. I'm working with patterns of variability, and this is my side, assessing that. But one would expect that modeling the location, choosing the locations of wind farms based on quantitative information regarding the variability on each scale and in each place would really change the picture, would lead us to a more efficient, to more efficient power. Elevation makes a big difference, that's true. All the experiments that I did here don't take elevation into consideration. Now I've started a collaboration with our colleagues from engineering, and they have contacts to a wind energy company that agreed to provide information, and not just information, wind speed records with a very high sampling rate for 5, 10, 15, 25, 35, I don't know how many meters. In all these intervals. So I will be able to assess implications of height also. So I'm looking forward to that. That's a very good question, a very good point. I'm looking forward to studying that. I haven't seen that done. Thank you. Any other questions?
You didn't do all that work just for this talk today, I hope.
Yeah, last night. Actually,
That's impressive.
the slideshow, yes. Almost. No, this is not published. It was presented to a couple of places in terms of research, but the publication is only coming.
Any final questions? If not, thank you all very much. Jason and Cynthia.
Yes.
Very
Thank you.
enjoyable.
Thank you.